good morning, not morning. Hey, I caught that, so that's good. Okay, so test 2, done. I still have to mark the long answer, right? And so your mark at the end is probably scary looking because there's 13 marks missing. So once I mark the long answer, then I'll add that and it'll be part of that. I think it was a total of 65 or something. So I will mark the long answer and add that grade and add it to your current total, right? So the absolute total is out of 65, I think, but you're all missing 13 of those, and that's a lot, right? So, so just don't be scared. It's going to get better, assuming that your long answer was good, which I expect that it was. It was on the long side, so if I end up having to make adjustments, I'll do that. I usually just make sure that the highest grade gets 100%. So if no one was able to get 100% naturally, then I just kind of cut the total, and that's how I usually do it. So we'll hold off and see what happens once I mark that long answer. All right, so you've got, it's okay. It's out of your hands now. You've done it. You can cross it off your list. Now it's on me. All right, so today we're going to start chapter 8, and chapter 8 is probably, I'm going to go out on a limb and say it's the most fun chapter that there is, because although we will be able to do some hypothesis testing and we'll be able to build confidence interval, it's not the focus of this chapter. And so we kind of move away from inference a little bit, not much, but in the formal sense, we move away from it, and we get to fit lines of best fit to scatter plots. And so usually it's a really fun chapter to end on, and it is our last week together, and I can't believe it. Time just kind of slipped through our fingers, but our final exam is on December 17th, I think at 9, I want to say, at 9, well, until 12 PST. Okay, we'll talk more about that. Obviously, we won't be able to go through any questions on Friday, but I do want to have a final exam review day on Friday. Final exam review day on Friday. Yeah. I'll put quotes around the review because we won't do any questions, but I just want to highlight the things to focus on for you to study. Okay, but again, those the assignments you've been working on, as well as the tests, but I think should be able to see the correlation, which we'll talk about today, between the test questions and the assignment questions. And so those will be good for studying. Okay, so I'll kind of parking lot that until Friday, although it's all I want to talk about, so I'm going to try not to. Okay, so let's see here. So chapter 8, we're starting regression. Chapter 8 is regression. Okay, so regression is just a line of best fit. And just before class, I posted, these are kind of outdated, but not the material, just the labels here. So it's chapter 8. And I guess I can just copy here. So it is a lot of material that we're going to kind of run through here. And maybe what I'll do is I'll just remove this, delete, and I'll write the same thing, because it's important to not be scared of the word regression. When you hear regression, I want you to just think line of best fit, okay? Line of best fit. Okay. So yeah, I posted these notes, and because there's a lot of kind of theoretical ground to cover, we're gonna rely pretty heavily on these notes, and then hopefully we'll kind of work our way through it, and then on Thursday, so our next class, I'll show you guys some output that we would be expected to read. I also posted your last assignment. Maybe I'll bump this down here. Assignment number 14, I think it was. It's relatively short, so don't worry, which is on regression. Will be your last assignment. Okay. It's possible that I'll end up removing the last question, but I think we'll be able to cover at least, you know, the basics of multiple regression. So what we're going to start with is if we have one explanatory variable. So, and then we can expand that and talk about multiple explanatory variables, but that's in the next chapter. So regression is modeling a relationship between two variables. And so we're going to focus on two numerical variables, although I'll mention what to do if you have a categorical explanatory variable. And then there are methods for modeling a categorical response variable, but that's logistic regression typically, and so we'll save that. I saw that a lot of you have signed up for Stat 240, so that'll be really fun, and we'll talk about that there. So we'll kind of save some of the good stuff for later, I guess. So let's see here. Usually we have some sort of relationship, and let's see here. Usually we'll have a relationship between two numerical variables. And so here, this is talking about the percentage in poverty of a state and the percentage of high school graduates that each state has. And so, but here, this is, you can even just kind of block this out, the axis labels right now, because we'll talk about them more. But in general, to visualize the relationship between two variables, then we need to have a scatter plot. Okay, so we use a scatter plot to visualize the relationship between two numerical variables. And I want to just grab oh, I'm gonna bump that down. Okay. Keep it on one page, try to at least. Okay, hey. There. Okay, so what we're gonna have is we're going to have some response variable, which is on the y-axis. And in general, let me see if I can find a different color here. The response variable is the thing that we're interested in, right? We're interested in and eventually predicting the y value, right? So the response variable. Right? Whereas here, an explanatory variable, remember I like to use the word explanatory, but there are other terms that we could use. It goes on the x-axis, and that's because, or not because, but I like the term explanatory variable because it emphasizes that it goes on the x-axis, right? And so I have a little note here that we could use the terms dependent variable for the y-axis and independent variable for the x-axis, but I prefer to talk about explanatory variables and response variables. We could even call the variable on the x-axis the predictor. Okay. So we could also call the x variable the predictor. Okay. So what we need to talk about is, okay, well, there's some relationship here. Sorry. There's some relationship between x and y. So in general here, let's just talk about x and y. All right, let's not worry too much about what they are right now. Okay, and so we have this scatter plot, and we understand that each point represents an observation in our data. Okay, so here, this point here is one observation in our data, right? I have some x component and I have a y component, right? And I'm gonna do my best here. That's not very straight. Maybe I can do a little bit better than that using different line type, maybe. How about that? How about them apples? Hey, it's not straightening out. Okay, well, whatever. All right, so maybe this is at 16.4 roughly. And this might be, looking at the scale here, 85 to, hey, maybe this 16 to 18, 17, 16, let's say 16 and a half. 85 to 90, 87 and a half, 86, let's call it, roughly 86. Okay. So this point would be at 86, 16.5, and really hard to see in that line type, so I'm going to change it back. Roughly 86, 16.5. Okay, so each point is going to have an x component and a y component, and that's what lets us map them on a scatter plot, of course. Okay, so our goal here is to try to model this relationship. Okay, so our ultimate goal is modeling this relationship. Okay, we see a pattern here, and we want to kind of have some way to summarize it. Okay, the general trend here looks like this. For this course, we're going to focus on linear models. Okay, so what we're going to be looking for is, do I have a straight line relationship? Okay, so I've got that all here. We'll introduce the problem as well. So the most common, and I mean, there are probably others, but the most common graphical display that we're going to use is a scatter plot. Okay, so there are three key things we want to look at when we see a scatter plot. Okay, and so what we want to look for is, we want to look at the form, right, or the shape, right? So remember, for a histogram, we talked about the shape, the center, and the spread, and that would give us a good summary of what it looked like. So now we're going to do the same or a similar thing with the scatter plot. Okay, so we look at the form, which I kind of think of as the shape. Okay, and so we're looking for patterns and potentially visible outliers, right? Because then you would mention those. Okay, and so we're going to want to see a straight line. So just like before, when we said, okay, when I look at a histogram, I'm hoping to see a normal distribution or an approximately normal distribution. Now, we're going to look and we're going to classify relationships as either linear or nonlinear. Okay, and so here, right, we're just looking for linear versus nonlinear. Okay, and if we have a linear relationship, then we can model it with a straight line, right? And you might remember y equals mx plus b, right? The equation of a straight line from some math course, or probably all math courses you've taken ever. And that's what we're going to leverage as well. So that's why we want a straight line relationship. Okay. If we have a linear relationship, we can use a straight line as our model. Right? So something like y equals mx plus b. Those aren't the exact ones that we're going to use, so I'm going to put little quotes around there, but kind of recall y equals mx plus b from another course, probably. I don't know, high school math, probably, hopefully. Right, and so y equals mx plus b, usually that rings a bell, even if you're not, recalling exactly what it is. If I asked you what's the slope, well, that's the m because it's attached to the x. What's the intercept? Well, that's the b, and there you have it. You know what the straight line equation is. We'll talk more about that, so don't worry. Kind of ripped through that, but I just want to get the juices going. Okay. So we're going to first and foremost look for a linear relationship. Can I reasonably model this with a straight line, right? If it's nonlinear, there are tools for that, but we are not going to consider them in this course. Okay, so you can deal with those. I'll talk about some of the options that we'll have, but we are not going to have to deal with those in this course. In fact, most relationships have a linear relationship, so that's really nice. We're also going to look at the strength of the relationship, and we're going to go from strong to weak. There are kind of grades in between there: moderately strong, moderately weak. But this is more of you looking at the relationship and telling me if it looks strong or if it looks weak. So it's more, so we will have measures like R squared. We're going to have measures of correlation. But for right now, we just want to talk about just visually, can we say that there's a strong relationship here? And then we're going to introduce, we'll actually have numerical measures of strength that we'll be able to talk about. So when I look at this scatter plot here, okay, I would say that this is a moderately strong relationship. The reason I'm leaning towards strong or moderately strong is because I see a pretty distinct pattern, right? And so as soon as you see a pattern of any sort, then you're talking about a moderately strong relationship. Okay, and then as these points get closer and closer together, so as they get tighter and tighter, then we can talk about, okay, here's a really strong relationship. And then in the other direction, if these points started spreading out more and more and more, then we start seeing just a cloud, right, of dots. And that's a weak relationship, because then there's no obvious place that you would place your line of best fit. You could put it straight across, you could put it straight down, you could put it straight up, and it doesn't actually do anything, right? It wouldn't really model the data because there's nothing to model. There's nothing happening in there. Okay, and so so we need to be able to look at a scatter plot and determine, okay, can I model this with a straight line? Or is there nothing going on? Okay. And I think I had, sorry, let me just crop top this here just for a little bit longer. Okay. So the strong versus weak, I want to clarify here. If you can see any sort of relationship, right, then you have a moderately strong relationship. So if you can see a, maybe I'll say some sort of distinct pattern, we will call it moderately strong. Okay. So as an example, just to have a look at some of these options, okay, we've got these 3 different scatter plots that I want to talk about. But the last thing that we'll talk about is whether a relationship is positive or negative. Okay, and so the direction of the relationship. So here we have a negative relationship, whereas here we have a positive relationship. Okay, so in general, we're going to have a negative relationship. Relationship is going to look like this, whereas a positive relationship is going to look like this. And maybe I'll use different colors here. Oops. There. Okay, so that's important to remember the direction that things are going, because what does it mean to have a negative relationship? It means that as X increases, your Y's are decreasing, right? As X increases, Y decreases. Hopefully you guys are okay with those shorthand arrows. Whereas a positive relationship is as X is increasing, Y is also increasing, right? So they're increasing together. So as X increases, Y also increases. Okay. So when you have a scatter plot, I'll give you a scatter plot then the first thing you need to do is you need to pick out, okay, my y-axis, that is my response variable. Sometimes you'll have to read a question and identify which is the response variable, which can be hard. Sometimes there's no distinct response variable versus explanatory variable, so then it doesn't really matter. But usually the one that we're interested in is going to be the response variable. And the response variable will always be the one that we're trying to predict. Okay, so what's really fun about regression is that we'll be able to use it to predict values, right? So that's where we're headed. Okay. So then we have to describe the relationship. To describe the relationship, we have to talk about those three things, right? The form, so is it linear or nonlinear? We're just going to break it up into linear versus nonlinear. Is it strong or is it weak? You're allowed to put in kind of your own spin on it, moderately strong, moderately weak. And like I said, we're going to have measurements for the strength as well as the direction of the relationship. But first we need to look at it so that we have something to check against, right? Do my numerical measures, do they make sense with what I'm seeing here, or did I do something wrong? Right, and then so positive and negative is just the direction, okay? So here we see a strong negative linear relationship, okay? So here, this is a strong negative linear relationship. Here, I have a moderately strong, I would say, because the dots are not quite as close to this line of best fit that has been added. We haven't talked about how to add that yet, but it's on here so we can look at it. And so there's more spread around that line of best fit. Even if we didn't have the line on there, you would probably visualize something like this, right? And then here we have, in the final one, we have a weak relationship. And you can see how, okay, so here's where the line of best fit ends up being, but it could have started down here and ended up here. Right, there's a relatively no slope, right, in the relationship. So here we have a moderately strong positive linear relationship. And here we have a weak, I mean, from the line, we can see it's negative. Let me clean that up. A weak negative linear relationship. We'll call it linear. There's no reason to fit any other model. So imagine if you think back to your math courses, right? If we have some sort of curvature, then one model that we know is the x squared model, right? A parabola. We can incorporate that here. So just like recognizing shapes like circles and squares and things like that, triangles. Now, when we see data, right, we're going to start to associate them with, okay, so I have a linear pattern, or if I have some sort of curvature, then I might, so that's for another course, but then I would maybe want to consider squaring my values, right, to capture that curvature. And there are lots of other things that we can do. But so it's important that, you know, we look at our data, we look at our scatter plot, and identify especially the form of the relationship, because that's going to tell us what a good model is going to be. Okay, so we've got this example here. So I want to introduce this one because this is the example that I'm going to rely on for, I think, the rest of this chapter mostly. Okay, but The scatter plot that we have, and let me bring it in again. And let me see. Oh, yeah. So the scatter plot shows the relationship between high school graduate rates in all 50 US states and DC. And they love to clarify that, but whatever. And the percent of residents who live below the poverty line, which is defined for this data set, any income below $23,050 for a family of 4 in 2012. So that is defined as the poverty line, okay? In the states in 2012. So we want to describe the relationship between percentage in poverty and the percentage of high school grads. Now, let me just bump this down a bit. Kind of before we describe the relationship, I want to talk about, okay, so the percentage in poverty, that's our response variable. And then the percentage of high school grads is our explanatory variable. And in this scenario, it doesn't really matter which one is on the x-axis and which one is on the y-axis, right? But in other scenarios, it will really matter. And so usually the one that we want to predict values of is on the y-axis. So in this example, the x and y variables are interchangeable. Yeah, explanatory for the x. So in this case, so yeah, exactly. It's to help you remember. So in this example, right, we could predict the percentage of high school grads in a state given the percentage in poverty, right? And so here we can interchange these, and it doesn't really matter. It depends on the question that we want to do. But in general, okay, the variable that we want to predict will go on the x, or sorry, on, let's flub that up, y-axis. Will go on our y-axis and be the response variable. Okay. So here, if we look at the relationship, and we have to describe this relationship, we've said that it's a moderately strong negative linear relationship. Okay, saying that it's linear, that's what lets us model it with a straight line. So don't go telling me it's nonlinear and then go fitting a straight line. That doesn't make sense, right? And so you want to be really careful. You want to make sure that you have a linear relationship or a reasonably linear relationship. And what you want to do is you just want to look at just kind of, you know, the general situation here looks linear, right? Kind of broad strokes here. And so our goal eventually is to fit a model so that we can predict the percentage in poverty as long as we have the percentage of high school grads in a state. So if we introduce a new state, which I mean, seems weird, but right, in this case, if we introduce a new state and all we know is the percentage of high school grads, then we can use the line of best fit as a best guess at what the percentage in poverty would be. Okay. So I like to show, of course, you let all these stats and math nerds have their way with free open source packages. So of course someone makes a Caterplot package, which is a scatter plot but with cats instead of dots. And so here the Caterplot package. So it replaces, of course, this is just a random plot, but you can replace all your dots with, it is for R. So, and I've got the code in those notes. Yeah, so pretty cute, pretty fun. And so it replaces all the dots with cats. There's no point in doing it. 0 point. But you can even do this little guy. Cute. And I can't remember the name of them. Steve told me one time, but I can't remember. Yeah. Yeah, is it Meowcat? I can't remember. Anyways, just for fun. And so here's the Caterplot code that I've used. And maybe the Caterplots don't need to be so big, but you might have to check. And what I can do is I can post the code, because this is just from before. This is from a long time ago, so they might have updated it. Probably not. I mean, once you build a good Caterplot package, then why change it? But I think his name's David Gibbs who made it. So you can run this code if you want to, and it should produce. I'm getting a couple of errors, I think, because I am showing the install GitHub Caterplots, which you wouldn't need to run every time. But anyways, just something fun that you can play around with. And maybe you always want your scatter plots to be Caterplots. You never want to see anything else. All right. Just kind of fun. Yeah, it's getting it. I don't know. It was giving me all this junk. Nyancat. Yeah. Very important, but really fun. So anyways, so you can play around with that. There's lots of fun things that you can do. And I think it's especially fun because it's, it's free for everyone and people are building packages. And that is one of the reasons that R is becoming kind of the most popular programming language. Just as a side note, the only reason you wouldn't use R is because it's not guaranteed, but we can place our trust in R. But some government agencies, a lot of government agencies are using R now, whereas they weren't before because they felt like they would have to pay for something for it to be good, but turns out you don't. If you just make it free for everyone to use, then people are supplying more updated libraries than they are to SPSS, or S is the paid version of R. I know, weird. I've never used S because I've only used R, and it works just fine. That's just a little background. All right. So just as kind of a guideline here, we want our relationship to be linear, right? Because, well, like I said, it's the most common thing that we're going to see. And it means that we can fit a straight line to the data points, right? And so that's what we call a regression. We'll be able to measure the strength of the relationship as well as the direction of the relationship using the correlation. Okay, and correlation is one of those things that we use in our everyday language. But here we're going to apply it in a mathematical sense. So it is a mathematical measurement, but it is exactly what we think it is, right? It's a mathematical measurement of the strength and the direction of a relationship, of a linear relationship. So that's kind of tricky, right? And then we can measure the variability, and that's going to be using R squared. And then, of course, the moneymaker is we're going to be able to predict future values using a linear model. Now, when I say future, I don't actually mean in time, I just mean some unseen value. Okay. So we've talked about, okay, we need to have a linear model, and that's great. But before we kind of move on from that, what if we don't have a linear model, right? So what if you see a relationship that's not linear? Okay. So what you could do is you could look at the histogram of each of the variables that you're looking at. And if you see that either of them are skewed or potentially both of them are skewed, then you're going to see a non-linear relationship in your scatter plot. Okay. And so that's just a fact. That's not helpful because it doesn't tell us what to do. But what we can do is we could apply a transformation to the data. And so, well, I missed a comment. Oh yeah, so if the R squared, so R squared only applies to linear models. Okay, so so then if we have a nonlinear model, then we're going to see a low correlation value, okay, which leads us to the R squared, but we'll kind of parking lot that. So what we could do, okay, so we could apply a transformation to the data, right? It means we can do things like take, instead of just X, we could apply X squared in our model, but now we have this curvature, right? We know, we remember sort of, right? X squared, okay, that's a parabola, uh-oh, right? I'm no longer in linear territory. Okay, and so that's one of our options. Okay, another option, especially if you're in the biology stream of this course, then you can apply the natural logarithm. So a lot of the time for chemistry and biology, we apply a natural log, so the ln, and we use the natural log instead of log base 10. Log base 10 is for things like frequency. So physics uses log base 10 often, but for us in the other sciences, so biology, chemistry, then we end up using log base E, so the natural log. So that's one of the options. So we can square things, we can take the log base E of something, and I'm being purposely vague here because we're not going to do it, okay? One thing, so the problem and why we're not doing it in this course is because if we've applied a transformation, then you have to take those transformations into account when you are interpreting your results, and that can make it kind of difficult, okay? And so for these reasons, we save this for a later course. Okay, but just good to know what to do, that there are options, right? We can transform the data. We can look at other models, nonlinear models, and so on and so forth. Keep having to bump this guy down, but we'll get there eventually. Okay. So we've talked about, okay, if I have a scatter plot and I look at it, I'm looking at the shape. Can I argue that I have a linear relationship so that I can fit it with a linear model? And then what type of relationship am I looking at, right? The strength and the direction. And just like we had numerical measures for the center and the spread, when we looked at a histogram, right, we could look at it and determine the shape. And then we talked about the center, and then we talked about the spread. And then we said, okay, well, we can actually have numerical measures for the center and the spread. So now we're going to introduce a numerical measure for the direction and the strength of the relationship. Now, I want to add something here. It has to be a linear relationship. For a linear relationship, and it's called the correlation, right? So the correlation has a few key properties that we need to remember, and do this, grab this whole thing. Of course, this is not something that you're going to have to calculate by hand. Okay. And I'll bring in the side note as well. So the correlation is denoted by R, a lowercase r typically. It can also be denoted by a capital R, but don't confuse it. The context will tell you which one you're talking about, the software or the correlation. Okay, and so in general, the formula here is R is the sum of the xy's. So you would have a column of your x's, a column of your y's. And there is a problem on your assignment where you have to actually use these summations. So you will have to use this formula once, but that's just because I want you to see what's happening. Okay, and because it's an assignment, you can refer back to your notes and you can kind of take your time. It's not something I would expect you to do on a test, right? So on the final exam, I'll just give you the correlation. Okay, but it is nice to know that you could do it kind of by hand, right? Of course, we'll use software to do it, but so what you would have in your data set is you would have an X column and then a Y column. And then what you would need for each of these summations is you would need to make a new column where you multiply X and Y together. And then you add all those up, and that's the sum of X times Y. Okay, then you'd want to subtract your n, which is your sample size. So how many pairs do you have? Times x bar, that's easy. You can just find the mean of the x's, times y bar, that's the mean of your y's. And then you've got these square roots of x squared, which means, okay, now I have to, so the sum of x squared, to get there, I have to have another column of my x's squared. So you take each x, and you square it and you record it, and then you add them up. And that's the summation here. And then minus the sample size times x bar squared, and then square root it, and then do the same thing for the y's. And it's all just so much work. You're gonna have to do it once on the assignment, and then that's it. So if you have, the covariance, which is SXY, SXY is the covariance, and maybe I'll highlight that here as well. Okay, if you have SXY, then what we need is we take the covariance divided by the standard deviation of your x's times the standard deviation of your y's. So it's important to keep track of which one is your x variable and which one is your y variable, right? Because later on, we're going to take a fraction of the two, and if you have them swapped incorrectly, then it's going to mess up all your values. Okay, and so here, what we get is this becomes the covariance divided by the standard deviation of x times the standard deviation of y. right? Because each column is going to have a mean and a standard deviation. Yeah. So the correlation has some key properties that we'll need to remember, right? So the correlation can take on values between -1 and +1, and that's it. Okay. And so as the correlation moves away from 0, then the strength of that relationship becomes stronger and stronger and stronger. If you're on the negative side, then you have a negative relationship. And if you're on the positive side, then you have a positive relationship. Okay. And so here, again, bump it down. It's going to take us, not much longer to get to that graphic, so I don't have to keep bumping it down. Oh, it doesn't keep going. It's a finite stretch between -1 and 1, centered on 0. And so what we're going to say is that, okay, between -1 and 1, so out towards -1 and 1, we have a perfectly strong relationship. So a relationship that has a correlation of 1 means that all the points are exactly on the same line. Okay, so here we have a positive relationship, whereas on this side we have a negative relationship. Okay. Just as a guideline, this is very rough, but correlations typically between -0.5 and 5, we would call them kind of weak. Now, if you're kind of on the border, like -4.5 or -0.45, sorry, we have to be between -1 and 1, then I would argue that it's, moderately weak or something like that. Okay. And so here, right, roughly at -0.5 and roughly at 0.5, here we have a weak relationship, whereas out here, I can call it strong, and also here we can have a strong negative relationship. Okay. So a correlation of 1, a correlation of ±1 means that all the points are exactly on the line. Means all points are exactly on the line, meaning that they're perfectly correlated. Okay. A lot of physics experiments are going to have, because, things like gravity and, I don't know, force and whatever are so predictable, then we get these super, super high correlations, if not 1. Whereas, in biology, we're going to be happy with a correlation of 60% or 0.6. Skip to r². But anyways, we're gonna be happy with relatively low correlations and say, hey, there's something going on here. Whereas, so it depends on what field you're in. Whereas if you're in physics, you would say, oh, there's nothing happening here. So that kind of depends on what field you're in. Okay, but so those key aspects of correlation are going to help us summarize the direction and the strength of a linear relationship. Okay. So here's a little example we can look at. So we've got these options and we want to pick what the best guess for the correlation is for this graph. And it's the same one that we've been looking at. And so first things first, right? We need to consider everything that we know about the correlation, right? If I see a negative relationship, then my correlation has to be negative, right? Because I have a negative relationship. And so right away, I can eliminate two of these options, right? Negative relationship. Yeah. Looking at my other options, I have three options left. I also know that the correlation can't be beyond plus or minus 1, right? So I know negative 1.5 is not an option. Hey, nice. Right, and so here, oops. Copy and, oh, come on. Oh. Supposed to make it easier. I should have just written it out. Come on. It's hidden behind there. I know it is. How do I grab it? Okay. It's because I have the text on there, making a mess. How about this? I'm not gonna mess around with it anymore. Relationship. And just to play it safe, I'm going to paste an image of it over top and forget all about it. What a waste. Okay. All right. And what a mess. Okay, so there. This one's not an option because it can't be beyond plus minus 1. It's supposed to be a quick, easy exercise. And you guys have already answered it. So what am I doing here? Anyways, and because we see some sort of relationship, then it has to be more than negative 0.1. So although this is a negative relationship, a negative 0.1 correlation would show very, very little. So remember that first cloud that we saw where the line could kind of go anywhere, that would be a correlation of 0.1 or negative 0.1. We see a relationship. So the correlation must be kind of larger than negative 0.5. And I mean larger in the negative direction than the absolute value of negative 0.5. So then here, oh yeah, so for 0.1, yeah, exactly. So for a correlation of 0.1, and the correlation will play a role in our slope. So if that helps you, then you can think of it that way. So if you have a small correlation, then you have a slope that's close to 0. Okay, and so we'll see how that relationship comes about. But so the most reasonable guess for the correlation here would be negative 0.75. So then another thing we could talk about that maybe I didn't need. That image I have is going to come into play really soon. Which of the following has the strongest correlation? Okay, and so what we see, so a correlation coefficient closest to +1 or -1. Now, what I want you to be really careful of is the correlation only applies to straight lines, right? And so here, although we have a really strong non-linear relationship, so for A, we have a strong non-linear relationship. So if I were to fit a line, right, if I were to model this with a straight line, it would likely look something like this. Okay. Now, the correlation tells me how close to the line everything is, you know, in kind of brief terms here. And we notice that the points aren't actually hovering around the line at all, except in these two key locations. So that's what's going to make the correlation really low, right? So the correlation here, correlation will be small or will be low, since very few of the points are scattered around the line. Okay, so now it's just a matter of, okay, making sure I have a linear relationship. B looks like a linear relationship. C, I guess, looks like a linear relationship, so that's good. And then D looks like a linear relationship as well. But in terms of the one with the strongest linear relationship, that's going to be B. Kind of a, you know, hard to say between B and D, but we see some kind of a little bit of departure from the line in D that we don't see in B. Okay, so that's good. Now, some other correlations, because it can be kind of hard to know what the correlations would look like, right? How am I supposed to know what a correlation of 0.33 looks like? Well, it would look like this, right? So here, notice that we're not really seeing a pattern. I would maybe argue that, okay, well, they're all kind of pushed up against the line here, but on the bottom side, you know, maybe not so much. Right? Maybe like this potentially, right? But we could also block it off like this, and it's really hard to tell which way it's going, right? And so here we see more of a pattern. So this is a correlation of 0.69. So as soon as you see some sort of pattern, then you would say you have a moderately strong relationship. Because remember, we said, okay, just as a guideline, a correlation greater than 0.5 or negative 0.5, so beyond 0.5, we're going to consider strong, right? Or moderately strong. So here we would say a moderately strong relationship. That's confirmed with the correlation of 0.69. So notice also that the textbook likes to use capital R for the correlation. Most other textbooks, and this is like the one weird thing, I'm sure they have a reason for doing it, but this is the one kind of thing that they do that I don't know, necessarily agree with. I'm sure there's a reason, but typically we use a lowercase r for the correlation. Anyways, doesn't matter. Here's a correlation of 0.98, right? And then of course, a +1 relationship is this exactly straight line pattern. And same thing with -1, right? And so we can look through and just kind of have an idea of what these correlations would look like, right? So here we have a correlation of 0.08, very, very close to 0. right? And so, and you can see there's no reasonable where, there's no obvious place where you would place your line of best fit here. So that's why the correlation is so low, kind of floating around. And there's no relationship here, right? When we look at a correlation of 0.08, it doesn't seem to matter what my X value is, right? And so that's what we're communicating with the correlation is, does knowing X tell me something about the Y, right? Because it doesn't seem to matter if my X is here, right? So if I put my line of best fit maybe like this, if my X is here, then this is my predicted value of Y. But also if my X is way out here, then my predicted value of Y stays the same. So there's no relationship here. Okay, good. Finally got to use that one. I've been bumping around. Oh yeah, and so let's see here. One thing that's going to be really, really, really important is that correlation. So just because you have a correlation, it doesn't mean there's causation. Okay, and that's going to be really, really important. And my my supervisor for my master's, I had him for my my first stats course. It was a Stat 230 actually, and he just stood at the front of the class yelling, "Correlation does not imply causation," and he would just yell it at us. And I guess I did too, right then and there, but in a more jokey way. But anyway, so it's really, really important that we never say causation, right? The only way that we can establish causation is through an experiment, right? A completely controlled experiment. So I do want to add that here. The only way to establish causation is through a completely controlled experiment. Because there are often other things going on that we can't control, right? That we are not taking into account in our scatter plot or later in our model, right? That might be affecting the outcomes. So for example, just because two things are correlated, which you're allowed to say they're associated, okay? So here, correlated, there's an association, so you're allowed to say association, but you're not allowed to say causation, okay? It does not mean that one variable causes a change in the other. So for example, if we think about ice cream sales, would be positively correlated and probably pretty strong with the temperatures outside. So as the temperature increases, then you expect your ice cream sales to increase as well. But we can't say something silly like, oh, it's getting colder. Oh, don't worry, we can just sell more ice cream. Well, that doesn't work, right? And so, so that's why that's an obvious case. If we don't know so much about the variables that we're talking about, then we might end up saying something silly like that. We don't know it because we have this understanding of, oh, that doesn't make sense. Whereas we might be analyzing data where we don't have that understanding yet, right? And so that's why you never want to say that there's causation. You can say there's an association, but you can never say that there's causation. And so I like this little comic. I used to think correlation implied causation. Then I took a stats class, now I don't. Sounds like the class helped. Well, maybe. Anyways. So pretty cute. But yeah, so we can say that there's an association, but not a causation. Okay. So let's talk about how are we going to fit this line of best fit. Now, there are lots of methods that we could use, but the least squares regression line is the most commonly used and the one that is kind of widely accepted as the version of a linear model that we would apply. Okay, and so we have this idea of, okay, I've got a scatter plot, I've got this line of best fit, and so how do we create this line of best fit? And the textbook does a weird thing where they introduce this line fit by eye, and I want to get away from that as soon as possible. So I don't want you to ever fit the line by eye. That seems weird. We have software that's going to fit the line for us, or we have calculations that we can do to develop this line. But the underbelly, I guess, of what we're doing is the least squares regression line. Now, what's kind of backwards, or at least hard to wrap your head around with the least squares regression line, is that it uses what we call the residuals. Now, the residuals are exactly what they sound like. They're the distance from each point to the line of best fit, okay? But the least squares regression line minimizes the residuals, which seems reasonable, right? Where would you put the line? Well, where you're able to be as close to as many points as possible, right? But it becomes this kind of chicken and the egg situation where, okay, you need a line in order to find the residuals, but then we pick the line that has the smallest residuals, right? Or minimizes the residuals. So it's all going to hinge on the residuals, and we're going to use the residuals later as well. Okay, but I think for today, yeah, we'll just introduce the residuals. So so the line of best fit, we understand that reasonably no line, unless we have this perfect relationship, no line is going to pass through every single point on our graph. That's not going to happen if we have a straight line. And it's not something we should be going for anyways. And so what we can do is we can calculate this distance between an actual value and what we'll call the predicted value. Okay, so this is the first time that we're going to see this predicted value, and how we denote it is, let me just change the pen here, is with a y hat. The predicted value of y. We've seen hats before, but that was for the proportion, the sample proportion p hat. And so context is going to make it obvious which one is which. So now the hat in a regression context, so in a regression context, y hat means the predicted value of y. Value of y. Whereas in proportions, p hat means the sample proportion. It can mean the sample proportion, it can mean the pooled proportion, means the sample proportion. But in general, right, it's an estimate of the proportion. So the context is going to tell us which one is which and what the hat is doing. Okay, so it's really not that bad. It's just kind of weird when you initially see it. Hey, I thought I knew what a hat was, and now all of a sudden it means something else, but the context is going to lead you in the right direction. So the residual is usually denoted by E because R, of course, is the correlation. So that was kind of taken. And E is for the error term. Okay, so notice how we can think about the residuals as if they are the error of the line of best fit, right? How wrong was this line in its capturing the data? So the residual is, and maybe I'll say the residual is denoted by EI. We can just drop the E, or E subscript I denotes the residual for the ith observation. Okay, so the residual is denoted by E, and E is the error. Okay, and so what we have is we have the residual is the observed y minus the actual y. No, observed and the actual are the same. So the actual or observed y, I'll say that, and then the predicted y. Okay, so in notation, we're going to have E is y minus y hat. Okay. And so the least squares regression line minimizes the the sums of the squareds residuals, and we'll talk about why that is, but that's just the method that we're using. Okay, so just as a fun fact about residuals or errors, the sum of the residuals will always be 0 because that's how we fit our line. Okay, and so a least squares regression line minimizes the sums of the residuals. So with my last little bit of time to spare here, I want to talk about this theory because next day I'll show you how to calculate the slope and the intercept, but for now I just want to talk about what it is. So our goal is we want a line that has small residuals. That seems reasonable, right? Our line of best fit, if you had to fit it by eye, which I don't encourage you to do, but if you had to kind of approximate it, then what are you doing? Well, you're trying to minimize the distance from each of the points, right? So we've got a couple of options that we could consider, and of course it exists. We could minimize the sum of the magnitudes, so the absolute values of the residuals. But there are a couple of reasons we don't. The main one is, well, we look at the sum of the squared residuals because, well, it's the most commonly used, but also a residual twice as large as another is usually more than twice as bad. So if you think about a residual of 2, right, 2 squared is 4, but then if you double the residual, so if you have a residual of 4, all of a sudden 4 squared is 16. So that's going to weigh down your model. And so the least squares regression method, minimizes the sum of the squared residuals. Oh, I've done it again. There. Don't touch it, Emily. Okay. So what we're going to do is, and these lines got kind of bumped off, but what we're going to do is we're going to build a model And there's going to be, so just like before, there's a model for the population and a model for our sample. And I'll leave it there because I'm plumb out of time. But go ahead and read through the rest of those notes, and then I'll show you around on Thursday. If you have any questions, let me know. Otherwise, I'll see you on Thursday.